Howdy, howdy, this is Mr. Potter, and welcome to day 15 of our logic. Today we're going to be talking about quantified statements, how we go about negating them, how to do compound quantified statements, and how to prove arguments using quantified statements. So let's get started. First thing I want to do is a real quick recap. We talked about last time that when we want to do the negation of a universal statement, we end up with an existential statement. But I wanted to talk about where that actually comes from. So let's say that I have universal x, and I've got some predicate p, and I've got some predicate q. And I want to do the negation of this quantified statement. Well, we know that the negation of a universal is an existential, so I will end up with an existential, but I still have to take the negation of this conditional. And I remember from a rule called denying the consequent that the negation of a conditional actually gives me a conjunction. And because we're denying the consequent is the statement that gets negated, not my antecedent. That stays the same. So what we end up with is an existential px conjunction negation qx. And remember when we talked about quantified statements last time, existentials and conjunctions go together. So this is how we get the negation of a universal to be an existential. Working the other way, coming out with the negation of an existential to get a universal, takes a little bit more work. But let's say that we have an existential x, and I've got px conjunction qx, and I want to take the negation of this quantified statement. Well, I know that the negation of an existential is a universal, but I still need to take the negation of this conjunction. And we know from De Morgan's law that the negation of a conjunction should give me a disjunction where both terms get negated. But this is not at all what we expect from a universal. From a universal, we expect a conditional. So the question is, how do we go about changing a disjunction to a conditional and denying the antecedent? The rule that we used in our previous talk on two-column proofs is our key. So what we're going to be doing here is, if I deny the antecedent already is negated, but I want the opposite of something that's negated, which means I'm taking the not out by double negation. But this still has a negated consequent negation qx. So a two-step process. One step using De Morgan's law to change the conjunction to a disjunction, which negates both terms, and then changing a disjunction to a conditional using denying the antecedent. So this is how the negation of a universal comes to be an existential, or the negation of an existential comes out to be a universal. And what this allows us to do is to take the negation of these quantified statements that I've got here. I know that the negation of a universal, dogs, conditional, fleas, should be an existential. And remember that I'm not saying they're not dogs. I'm saying they don't have fleas. So I'm negating the fleas part of it. And so I end up with some dogs don't have fleas. And another way I could have said this is I could say not all dogs have fleas. So here I've got the negation of a universal gives me an existential. Here I have an existential. Some dogs have fleas. They are a dog and they have fleas. And I want to negate this existential. Well, I know that this should give me a universal, and I'm denying the consequence, so only f of x changes, d of x stays the same. And so I end up with all dogs don't have fleas. Or another way I could have said that is no dogs have fleas. What's a little bit trickier is when I already have a negation in the statement, like these last two examples that I have. Notice I'm saying not all dogs have fleas. A negation puts a not into a sentence, or it takes a not out. So I'm expecting my answer to not have the word not in it. But what I've got is an existential. I am saying they're dogs. They just don't have fleas. But I'm taking the negation of this, which should give me a universal, and denying the consequent changes not the antecedent, but the consequent, but it already had a negation. So I need to get rid of the negation, and I end up with the unnegated predicate fx. And so this ends up being all dogs. dogs have fleas. And I run into a similar task down here when I have this universal dx conditional negation fx. No dogs have fleas that I'm trying to negate. And this is logically equivalent to an existential. They are dogs, but I'm negating something that already has negation fx, so I end up with the unnegated predicate fx, which gives me some dogs have fleas. Notice that both of these statements don't have an alternate form because my statement has no negations in it at the very end. Because these statements had negations in them, I had a not that had to be put somewhere. And it either got put in between the predicates, or it was used at the beginning to explain what's happening. What the second predicate was missing from the first. And that happened in both of these situations where I had a negation in my final sentence. But if I don't end up with a negation in my final expression, I only end up with one form. So, before we start talking about compound quantified statements, I want to do a real quick recap. The idea is that if I had a sentence that had something and something else, and I wanted to find the negation of that compound statement, I know that the negation of a conjunction should give me a disjunction where each of these terms get negated, my first and second statement. And similarly with De Morgan's law, if I want to take the negation of an or sentence, I end up with an and sentence where each of these statements has been negated. The only thing that was different was when I was dealing with denying the consequent. If I had a conditional if something, then something else, this ended up changing to an and statement. And only the second statement, only my consequent got negated. My antecedent didn't get negated. So if I have a statement like this, which already has an and in it, and I want to find the negation of all cats have whiskers and some dogs have fleas, the negation of a conjunction should give me a disjunction. So I should end up with an or. The negation of a universal is an existential, so I should end up with some cats. And remember that when I take the negation of quantified statement, it's the second predicate that changes. Some cats don't have whiskers. Or, and now I need to take the negation of the second statement. The negation of a existential is a universal, all dogs. And when I deny the consequent, I'm saying that they don't have fleas. So the negation of a conjunction gives me a disjunction by De Morgan's law. Similarly, the negation of a disjunction gives me a conjunction, and. But I'm still taking the negation of this first statement, which we've just done right here. Some cats don't have whiskers. And I'm also taking this negation of the second statement, which I already have. Some dogs have fleas becomes all dogs don't have fleas. The only thing that's different here is the conditional. If all cats have whiskers, then some dogs have fleas. And using denying the consequent, this becomes a conjunction. But if I'm denying the consequent, this antecedent here doesn't get negated at all. We're just going to transcribe it. All cats have whiskers. It doesn't change. The only thing that does change is this consequent, which of course we've already done twice already. All dogs don't have fleas. So if I'm going to take the negation of a quantified compound statement, a statement that has and, or if then, between the two quantified statements, I need to go back to De Morgan's law, or go back to denying the consequent to fix those statements. The last thing that I want to talk about today is the topic of instantiation. So I need to give a definition for that. Instantiation is a statement that replaces an unknown subject. That's a variable. With a known subject. Okay. An instantiation is a statement that replaces an unknown variable subject with a known subject. So in this quantified statement down here, I'm doing universal X. All dogs have fleas. And so X is an unknown value. That's our variable. But in the very next sentence, we know that we're not talking about all dogs. We're concerned about one dog, one very specific dog. And the subject of this sentence is Fido. So if we're talking about Fido, Fido is the subject of this predicate statement. DX is the statement is a dog. And so this ends up being D Fido. And so what I want to do in instantiation, I'm going to replace each of these X's with Fido. So I'm going to say D Fido conditional F Fido. And I'm not going to have a universal here because I'm not talking about all Fidos. I'm only interested in one very specific Fido. The Fido, that's the subject of our statement. And so what instantiation allows us to do is to take these quantified statements that are talking about all dogs, they're talking about some dogs, and end up talking about one very specific dog, which will allow us to do two-column proofs using quantified statements. And so here's our first example of a quantified proof using a quantified statement using two-column proofs. So what I've got here is I've got all cats have whiskers. And I'm saying that Sally is a cat. Who is a cat? Sally is the cat. That's who we're talking about. And she's a cat. My predicate would be C, Sally. Sally is a cat. Therefore, Sally has whiskers. Who has whiskers? Sally has whiskers. Sally has whiskers, so my predicate would be W, Sally. And notice that I've got premise 1, premise 2, and conclusion, which we're familiar with from our previous discussions of two-column proofs. So I'm going to construct my two columns, statements and reasons, and the first step is to list all of our premises. So I've got universal x, cx, conditional wx, and it's a premise. I've got my second step, which is C Sally, and it's a premise as well. Now, my first instinct is I'm supposed to take the conjunction of two statements. The problem is that this C Sally is not an exact match for CX. And so this isn't a pure case of modus ponens. What I have to do is I have to find something that matches exactly. And if I do instantiation, on step 1, then what I'm doing is I'm taking this premise and I'm replacing x, my unknown variable subject, with one very precise subject, Sally. Sally is a cat. Sally has whiskers. I'm replacing x with Sally. And this allows me to have a conditional that has an exact match to my statement. Now, this uses up statement 1. So I only have two statements left to do the conjunction of. And we're familiar with this, that when we're doing the conjunction of two statements, we always want our conditional to come first. So I want to do the conjunction of 3 and 2. And you see that this is much clearly a modus ponens argument, because this now exactly matches the antecedent that we have. And modus ponens says if the antecedents match, I end up with a copy of my consequent W Sally by the modus ponens argument. And that gives us a valid argument. So the purpose of instantiation is to be used in a two-column proof to replace my unknown variable subject with a very precise subject, so that my antecedent or my consequent will directly match it. And in this way, I'll be able to use modus ponens or modus tollens or hypothetical syllogism to put my conditional with another statement. So I want to do one more example here. I've got no ducks can whistle. This is a universal X. They are ducks. They just can't whistle. And by the way, our two-column proofs will only be using universals because universals have this conditional that we need so much. So this is our first premise. Universal X, dx, conditional negation wx. My second statement is Clara is a duck. Who's a duck? Clara's a duck. So my predicate is D Clara. And my conclusion is that Clara can't whistle. So my conclusion is who can't whistle? Clara can't whistle. And so I've got a two-column proof, statements and reasons. And I list my premises. I've got universal X, dx, conditional negation wx. That's the premise. My second premise, I've got D Clara. And that also is a premise. And the problem is that D Clara doesn't match anything that I have up here. I still have an unknown variable subject, which I really need to replace with Clara. And that's what instantiation does. So instead of saying dx, I'm going to say D Clara. And instead of saying negation wx, I'm going to say negation w Clara. Replacing x, replacing my unknown variable subject with who we're talking about, Clara. And notice that this gives me a perfect match here, so now I can use modus ponens or modus tollens or hypothetical syllogism. As long as they match, I'm good. I always want to put my conditional first, D Clara, conditional W Clara, conjunction D Clara, and this is the conjunction of 3 and 2. And this is a modus ponens argument. So this allows me to say negation W Clara, if there was a negation here. So I've got a valid argument. The key thing here is whenever I have quantified statements in a two-column proof, I'm going to want to take care of those x's. So then instead of dealing with an unknown variable subject, I'm dealing with a very precise subject. In this case, I'm talking about Clara. So that concludes our lecture for day 15. Thank you for watching. Have a good day.